Welcome back. Today we're going to be talking about wind and how wind starts to blow. And to do this, we're going to be looking at a pretty fundamental model of the atmosphere. Now, what is a model? Well, think about a model car or a model airplane or a model of something that you've probably seen. That model is a representation of the real object. That model car is a representation of a real car. That model airplane is a representation of a real airplane. And yet, if you take a look at that model, it is a much more simplified, much less complex version of the object that it's modeling. Well, meteorologists do this all the time when they talk about the atmosphere. The atmosphere is extremely complex, and therefore it's actually really hard to work with. Well, meteorologists create models to eliminate the most difficult to work with and also pretty insignificant complexities so that they can focus on the main things that are at play. A good example of a model that we've talked about so far this class is an air parcel. An air parcel is a pretty simplified model. And the reason why it's a model is because the air doesn't behave perfectly like we said with air parcels. But it's still a good model, a good representation of the way that air behaves. We eliminated many of the complexities by saying that, okay, the air cools adiabatically, and as it rises, it cools due to expansion or contraction, and doesn't cool due to anything else. It's completely isolated from its surroundings. Well, that was a simplification. And we do this many times in meteorology. We'll actually talk about several additional models as we progress throughout the quarter. The model that we're going to talk about today is what's called a column of air. So, a column of air is basically a long tube filled with air from the surface all the way to the top of the atmosphere. Now, in this column of air, we're going to have a few simple rules. These are our simplifications that allow us to work with this column of air. The first one is, unlike the real atmosphere, this column of air has uniform density. What that means is that air doesn't crowd near the surface like in the real atmosphere. If you remember in the last lecture, I talked about the pyramid where most of the air molecules hang out near the surface. The higher up you go, the less air there is. Here, in this air column, density is uniform, meaning that the same number of air molecules are present at any height in the atmosphere. Another key simplification is that the column's width stays the same as you go up and down the column. And then finally, we're going to assume for the moment that air doesn't leave the column or enter the column. Now we're going to talk about what happens to this column in a few scenarios. So, first off, let's talk about what air pressure is. Going back to this column, air pressure is the weight of the air above you. Here near the surface of the Earth, each one of these dots represents an air molecule. So here near the surface of the Earth, you have all of these air molecules above you. all of these air molecules above you. One of the reasons why air pressure decreases with height is the higher up you go into the atmosphere, the fewer of these air molecules you have above you. The fewer rows of these air molecules you have above you. So that's a good way of thinking about how air pressure decreases with height. Near the surface, you have all of these rows above you. The higher up you go, the fewer rows you have above you, the fewer molecules you have above you. Now, with that said, let's go back down to the surface of this column. Let's suppose that we actually added air to the column. So we ripped the top off the column and we poured more air molecules into it. How does that change the pressure at the surface? Well, since we've added air to the column, we've increased the weight of the air by adding more air. Hence, we've raised the pressure. On the other hand, let's say we rip off the top of the column and take some air molecules out. In that case, we've actually removed air from the column. Therefore, we've decreased the weight of the air and decreased the pressure. Now, that is if you add air, remove air. What about if you change the temperature of the column? Let's take this air column that we just talked about and let's heat it up. If you recall, when you warm a column up, or when you warm air up, what does it do? It rises, right? By warming the air in this column up, it rises, and therefore it becomes taller. So when we warm a column of air up, it becomes taller. On the other hand, if we cool the column, it's going to condense and shrink, and that's going to lead to a shorter column. With that said, I submit to you the two-column model of air pressure. And this is actually how wind blows. So this is going to be a really important model and one that I can guarantee you're going to be tested on. So make sure you're taking notes. So let's say we have two equal columns of air. Same heights, same widths, same surface pressures, therefore same number of molecules in each. And these two columns of air are standing right next to each other. We have air column 1 over here, air column 2 over here. Now let's play mad scientist with these columns a little bit. So, since they are the same height, and since they have the same density, as you rise in the column, the pressure changes are the same. For example, let's say we look at what the air pressure is at this particular height right here, where my mouse cursor is. To figure out what the air pressure is, simply count the number of dots above this cursor. If you go over to column 2, you'll notice that same number of dots, therefore same pressure. So pressure changes with height are identical between these two columns of air. Now let's play around with this a little bit. So let's change the temperature of each of these columns. So over city 1, let's cool the column down. Over city 2, let's warm the column up. Well, what actually happens is when you cool the air over city 1, that causes that column to shrink. It becomes a shorter column. On the other hand, when you warm column 2, that causes the column to expand. So column 1 shrinks, column 2 grows. Now, at the surface of the Earth, you still have, so if we're here at the surface of the Earth, you still have the same number of air molecules above you in either column. You still have 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, 66, 66, 72, 78, 84, 90, 96. You still have 96 dots above you in both columns. So at the surface, the air pressures are the same. Yet, look what happens if you go to an arbitrary height in each column. So let's go to the heights marked with these big black dots here. Count the number of dots above you at this dot, at this big black dot here in column 1. If you take a look, you only have, I'm going to just assume that we can count these, 6, 12, 18. On the other hand, over city 2, you have 6, 12, 18, 24, 30, and so on. So what actually happens is, in the cold column, as you rise in the atmosphere, air pressure decreases quicker. Why? Because all the air is bunched up closer to the ground. On the other hand, over column 2, because the air column has expanded, and because it's taller, you have higher pressure than you otherwise would have. The pressure over column 2, or the pressure at this height in column 2, is greater than it is in column 1. So, again, if you take a look, even though the surface pressures are the same, aloft, that's a fancy word for higher in the atmosphere, you actually get low pressure that's developed over the cold column and high pressure over the warm column. And again, this simply happens because at this arbitrary height, there's fewer air molecules above you in column 1 because column 1 shrunk, and more molecules above you in column 2 because column 2 grew. Now, the surface pressure hasn't quite changed yet. We're going to talk about what happens there in a moment. So, we have low pressure aloft over column 1, high pressure aloft over column 2. Now, with this said, cold air creates low pressure aloft. So the trough that we talked about in the last lecture, this is why it happens. On the other hand, warm air produces high pressure aloft. So this is that ridge that we talked about in the last lecture. Okay. This is all fine and dandy. But what actually happens if air is able to flow freely between these two columns? If we were to connect a hose allowing air to travel between these two columns? Well, Mother Nature hates imbalance. A natural system wants to achieve equilibrium. So, when you have high pressure in one area and low pressure in another area, air molecules will move in order to equalize those two pressures. So if we allowed air to travel up in the atmosphere, air would travel from column 2, this high pressure, to column 1, this low pressure. So air would travel from column 2 to column 1 here in the upper parts of the column. So aloft, air is traveling from the warm column to the cold column. This is what's called the pressure gradient force, and this is why we have wind. This is why we have wind. This is what starts wind up. Now, let's suppose, okay, so wind has traveled between this point in the warm column, air has traveled at this point in the warm column, over to this point in the cold column. And let's assume that enough air has traveled to where the two have equal air pressures at that height. Balance has been achieved, all is well, right? Not quite. You see, by adding air to column 1, even though we balanced pressures in the upper part of the atmosphere, we increased the pressure over column 1 at the surface. And by removing air from column 2, we decreased air pressure. We decreased air pressure over column 2. So even though we balanced pressures aloft, we raised pressures over column 1 at the surface, and we lowered pressures over column 2 at the surface. As a result, Mother Nature hates or loves equilibrium again, hates imbalance, and therefore winds again blow from high to low. And so you get this never-ending futile attempt to achieve equilibrium. Higher in the atmosphere, air is moving from the warm column to the cold column to equalize pressures aloft. Near the surface, that additional air is creating high pressure over column 1 and low pressure over column 2. And so air then travels back from column 1 to column 2. And you get this never-ending atmospheric circulation. Now, when I say never-ending, what I mean is if all the conditions were to remain the same, if we were to change nothing else, this process would continue to happen. Air would move aloft from column 2 to column 1 to balance out pressures aloft. However, that imbalances pressures at the surface, so air would then move from column 1 back to column 2. Take a moment and really think about what's happening here. So, starting out with 2 equal columns of air, same temperature, same everything. At the surface, they have the same pressure. As you warm one column and cool the other column, they both still have the same pressure at the surface. But because one column has cooled and shrunk, you have lower pressure aloft. Because the other one has expanded, you have high pressure aloft. Air then moves from that taller, warmer column to that shorter, cooler column, and that throws everything off at the surface. Now, in this week's activity, you're going to be talking a little bit about the sea breeze. So I'm not going to give you a big spoiler alert here, but the sea breeze is actually an application of this 2-column model. Over land, you have a warm column of air. Therefore, it expands, and you have high pressure aloft. Over the ocean, you have a cold column, which shrinks, and therefore you have low pressure aloft. Air then moves aloft from high to low, from land to the ocean, and that creates lower pressure at the surface over land, higher pressure over the surface of the ocean, and the rest is history. The opposite happens at night. At night, the land becomes the cooler column, and the air over the ocean becomes the warmer column. And so the circulation reverses at night. Now, with all that said, this pressure gradient force, this movement of air to achieve balance, is fundamental when we talk about wind. If we had no pressure gradient force, we would have no wind. That's right, you heard it here. If we had no pressure gradient force, we would have no wind. Well, the way that this works is because you have high pressure in one area, that means that you have a location with an abundance of air molecules aloft. On the other hand, if you have low pressure in another area, you have fewer air molecules aloft. If you had 2 tanks of water and you filled them to uneven heights and you connected a hose to them, they would balance each other out. Now, what I really want you to get about the pressure gradient force, not even connected to the 2-column model if you don't want to, is that wind blows from high to low. Wind blows from high to low to achieve balance. So, over the high pressure, there's an abundance of air molecules. Over the low pressure, there's fewer air molecules. Air moves from high to low in order to balance the two out. So this tank analogy is a good way of doing it. If you had 2 tanks of water with a hose connecting them, and you fill one up more than the other, water will move between the two until they'd have the same height. Now, what makes the difference between a gentle summer breeze and a wind that's ripping roofs off? Well, because the pressure gradient force is an attempt at achieving balance, in some cases, more effort, more energy, more strength goes into achieving this balance. So, when we talk about the pressure gradient force, there are actually 2 things that determine how strong it's going to be. These 2 things are the difference between high pressure and low pressure, how different the air pressure is between these two, and the distance between the high pressure and the low pressure. So the difference between high and low, and the distance between high and low. Here's how they affect the wind. They affect the wind using this simple equation: pressure gradient equals difference divided by distance. Now, how can we calculate this? Well, suppose we have these 2 isobars here, and we have a point on each one of the isobars. And these 2 isobars are 100 kilometers apart from each other. Well, the pressure gradient would be the difference divided by the distance. So, the difference between these 2 isobars is 4 millibars. The distance between these 2 isobars is 100 kilometers. So all we would do is we would take 4 millibars and divide it by 100 kilometers. And that is our pressure gradient. Now, take a moment and ask yourself this. What if I were to double the difference? Leave the distance alone, but what if I were to double the difference? Instead of 4 over 100, it would now be 8 over 100. So by increasing the difference, I've increased the pressure gradient. On the other hand, think about what would happen if instead of doubling the difference, I doubled the distance. Instead of 100 kilometers apart, let's say it's now 200 kilometers apart. Well, by doing that, what I've actually done is I've kept the difference the same, so 4 kilometers, But now the distance is 200 kilometers. So now I have 4 over 200. I've halved the pressure gradient force. So greater differences, stronger winds. Greater distances, weaker winds. Now, you're not going to have to calculate this on a test. What I do want you to know, though, is the way you can identify this on a weather map is simply by looking at how close the isobars are to each other. When the isobars are close to each other, that means you have a good difference over a small distance. That's a strong wind. On the other hand, if you have the isobars farther apart from each other, that represents a small change over a large area. That's a weaker wind. So where the isobars are close to each other, that's a strong wind. Where the isobars are far apart from each other, that's a weak wind. Now, let's apply this real quickly. This is an image of Hurricane Katrina, and each one of these lines is an isobar. If you notice, as you approach the center of Hurricane Katrina, these isobars get closer and closer and closer together. That's common. As they get closer together, the winds become really strong. And actually, at the center of Hurricane Katrina, wind speeds topped 175 miles per hour. So, the isobars are closest together near the center. Here's another example. This is Hurricane Sandy. Where are the winds the strongest? Well, they're the strongest where the isobars are closest together. If you actually take a look, on the southern end of the hurricane is where they were the closest together. And so here is where the winds are the strongest. Here is where the winds are the strongest. Now, in the next lecture, we're going to talk a little bit about the other two forces that affect the wind. Until then, I'm Terrence Mullins. Thank you for watching.